All right. Okay, let me share you again this textbook. Okay, boleh nampak Okay, the textbook. So we have CN. So how we calculate SN prime 0.5 SUT, CL, CG, CS, CT, CR. So CL you can look on this table 8.1. So this will be your CL. Okay. Okay, for shaft, depend on the case. Mainly we go for bending. Axial 1.0, 0.5. Okay, CL is a gradient factor. Gradient factor is a size factor. Okay. For example, like, okay, if you a gradient factor, it looks from this table 8.1, it is mentioned about all diameter. So most of the case for our fatigue analysis, mainly we focus on shaft. Normally, fatigue analysis, we focus a lot of cases on shaft, so it will be diameter. If the shaft diameter is about this range, if the diameter of the shaft, when you design or given in your assignment, the diameter of the shaft is given at that point where you have the critical bending moment, what is the diameter at that point, at that section? So if that diameter of that shaft is between 0.5 inch to or 10 millimeter to kalau is diameter from 10 millimeter to 50 millimeter, the bending is 0.9. Alright, its bending is 0.9. Okay, from this range. Alright, kalau the size between this range 10 millimeter to 50 millimeter, the gradient is 0.9. Okay, unless there is not given the diameter, for bending loading is 1.0. For axial loading on the shaft, this is the range 0. You can kalau the of axial loading 0.7 to 0.9. Kalau torsion, but most of the case the shaft ni I just need to highlight to we go for bending, because bending is the most critical on the shaft. Bending shaft. If the sorry, my mistake. 1.0 is less than 10 millimeter, you use 1 for bending loading. But for 10 to 50 will be 0.9. That will be the shaft pump class for the gradient factor. Understand? Or size factor. Okay, size factor. Okay, that is size factor. Kalau your shaft is less than 10 millimeter, it will be 1. But between 10 to 50, you will use 0.9. But it depends what type of loading that you focus on. But you think bending is the governed thing, it's much bigger than axial and torsion, so it will go for, you take this first column. All right? Okay, what about the CS? CS is the surface factor. Surface factor, okay, always given, or you design it, the shaft, you know shaft. Shaft, when they manufacture shaft normally is not just shaft. When they have a shaft, normally shaft ni kita go for step shaft. Shaft is not such straight plain diameter. But in example I need to discuss to you right after this is a plain diameter. For the step shaft, we go for the next meeting. I will be on next week. Right, okay. So this will be shaft. Normally shaft ni they will lace it. Shaft ni normally they have a plane. Normally the raw shaft is like this, the raw material is ready, then they will lace. Lasing machine, guys, they make it into step, because this will mount the pulley at this shoulder, will mount another pulley or gear, like that. So they will machine the shaft. If that, I mean the surface quality of the shaft, that we call the surface factor, the surface quality. If the surface is smooth, it's kind of like better. If the surface is rough, they have a lot kind of like a crack, something, the smoothness, the degree quality of the surface is not good, the factor is much reduced. So that is surface factor. So how do we check the surface factor? Class, are you watching or not? Class,
Yes, doctor.
can you see the textbook, right?
Yes.
Okay. Refer figure 8.13 to get the surface factor. Figure 8.13. Figure 8.13 in your chapter 8. Okay, here. If you look here, this is how you find the surface factor. For example, like, okay, how do I find it? Because normally shaft is lasing. Shaft is normally lasing. Sometimes in the question, your assignment it mentioned the shaft is not just machine, it kind of like polish. That is special case. Be careful about it. If polish, your surface factor is 1. CS is 1 because the surface quality is really, really high quality. But normally we go for machine. It's not given. Shaft is always go for machine. Lasing is machine. So this will be the line of the graph. Can you see the x-axis is your SU? What is SU, guys? SUT. You can find, guys, are you listening or not? This is SUT. SUT boleh dapat from table properties, right? Always in your question. Sorry, saya tak pakai. I'm not using tablet. Susah for me to write. This is your SUT. Class, do you understand me or not? SU is your SUT. Kan? Class, are you listening? SUT you boleh dapat daripada table, right? It's given the question, find SUT, that will be, okay, what SUT, be careful. This is KSI. Can you see the bottom scale? Gigapascal. This is 0.8 gigapascal, it means 0.8 gigapascal. So you convert to megapascal. So you got so put, for example, 800 megapascal is 0.8 gigapascal, right? Alright, so 0.8 you go for the value here. So you go, okay, what is the SUT value? This one in megapascal, you put here. Bring it up, class. Are you watching? Until it intersect. Okay, kalau it said the shaft is machine, it didn't say polish, so you will intersect here. Nampak tak, class? Sorry, my line is not good. The way I try to show you. You make a straight line here. Understand that? Okay, what is the value of your, let's say 850, right? Megapascal. So 0.85. Let's say 900. So, sorry, my line. You bring it up until it intersect with the machine or quadrant. So what is the value? Between 0.7, 0.8. So it will be 0.74. Clear tak, class? That's how you got 0.74. Clear, class?
Yeah.
Tulisan saya teruk sangat, saya tak faham. Okay, faham tak? You bring it here lah. You boleh lah, ini 0.7 scale, 0.8 scale, about 0.74. That's how you do. That's how you find the surface vector. Okay, that will be the surface vector. Depend the quality of the surface. Okay, what about the CT? CT is temperature. CT you just get from this table. Sometimes the question is saying that the temperature is less than 40 degrees, so your value is 1. All is 1. Either bending, loading, so torsion is 1. Or but it said that between range, let's say it's given that the temperature is greater than 40 degrees Celsius. So you say that it's 900 something or 1000. You put into this equation what the temperature given in the question, then you get the factor value here. But more of the case is less than 840 degrees Fahrenheit. Okay, unless special case memang ada higher temperature, depend on the situation. Okay, that is the temperature factor. Okay, CR is a reliability factor. Okay, always reliability factor is always given. If 90% reliability, so but 50% reliability, it means the reliability of your shaft, reliability in terms of reliability is if 50% is 1, 90%, the higher the value of reliability, it means 90%, 10% fail, 90% will pass, something like that, reliability. So the higher the reliability, the lower the value. Because the lower the, it means that the lower of the value of your, sorry, my mistake. If you expect the reliability to be high, the lower the value of your factor. Sorry guys, saya dah ngantuk already. Kalau the reliability you expect 99.9%, you mean you expect high expectancy on this specimen you analyze on, you putting high reliability like 99.9%, so the lower will be your factor. So your endurance limit will be, your SN will be lower. You mean that means your safety factor will become lower because your SN2 is denominator of your SN over sigma E is at the bottom, right? But if reliability is 50%, you expect low expectancy is 1. But most of the case like 90% is given equation or you assume it is 0.897. Understand, class? That is the same for both bending, axial, and torsion. Most of the case for the shaft, I just need to mention to you, it goes for first column, bending. But also sometimes it depends on the station. Sometimes the torsional stress is much bigger than bending. You go for all the middle column, the third column for torsion stress. Sometimes maybe the axial stress is much bigger than the bending. So you go for the column of the axial stress, right? Okay, that's it. CR, CL, CG, CS, CT, CR, CR, and all right. Okay, yang bottom ni tak apa. This one I explain to you later. That's about from SN curve. Okay, so that's why you put. Okay, can you see my live video boleh? Live video nampak class? Class. You there?
Nampak.
So you put the value. CS is the surface factor. Okay, surface factor, and CT is temperature factor. Okay, temperature factor, and CR is the reliability factor. All you get from table 8.5 measure. If you have the textbook, you kena bookmark, you kena highlight. Nanti during your exam, you bring your textbook, you have already marked. So easy for you to turn which page. Pasal you will refer this a lot. Reliability factor is for CR. So you all this thing and plus multiply 0.5 SUT. So that will be your SN value. That will be your endurance limit. So then you put the endurance limit and you calculate your sigma equivalent. So that will be your safety factor for your fatigue analysis. That's all for fatigue analysis. But first part, part 1, fatigue analysis. That's how you do it. Understand, class? Clear tak? Class?
Clear.
That's why. Pasal the point of analysis, we need to find the safety factor. Greater than 1 means safe lah. Okay. Endurance limit is this formula as sigma E as what you did before. Okay. How to calculate sigma E kan? So that will be your denominator. Endurance limit is no longer SY, it's SN, even lower than that. So this I explained to you only part 1. Okay, class. I don't think so. You kalau I didn't give you example, you quite hard for you to understand. Okay, guys, what I want you to do, you look at the e-learning. Okay, I share you e-learning. E-learning, you look at the ni exercise 1 fatigue juvenile buka ni. Kelas open e-learning topic 5. One exercise fatigue juvenile with solution. Cepat kelas sikit, kita ada lagi setengah jam ni les. Ini 2 jam je kan. Tuesday dah lah tak ada kelas. Tu saya risau juga ni. Lepas tu next class will be on Sunday ada kelas kan? Online kan kelas? Boleh Ya cakap Sunday pun tak nak kelas pula. Kelas. Are you listening or not? Tuesday no class, but Sunday kita ada kelas. Understand tak? Sunday. This coming Sunday after Raya kan? We have class online Boleh
Doktor.
Pasal buat. Kalau tidak nanti balik nanti kan I think tak cukup masa kan. Pasal cuma Tuesday saja kita tak ada kelas Alright. Okay, dah buka kelas dia one. The ni. One exercise class. Ni one, this one. Have you opened it?
Dah buka. Yes.
Right. Okay, I just discuss one sample example. Okay, I share you ni. Okay, and that one, no? Okay, boleh nampak kan yang saya share ni?
Boleh.
Okay, kita I don't want to, if you look here, we have some example and solution. I don't want to you look at the first one. This one, first one ni dia ada, because that is certain factor that I have not explained to you about the fatigue, stress, concentration factor. Pasal any shoulder, macam first exercise one, if you look exercise, okay, this is typical shaft analysis. We have force loading. We will do we find safety factor based on this loading because the shaft is rotating. Fatigue analysis. Tapi bila you plot, okay, this kind, for example, question 1, you will plot because we have only one plane here because we don't have two planes. Like we discussed before, we have two planes and pulley. The cos, the sine, but this one is only one plane, maybe xz plane or xy plane. So what you would do is typical shear diagram like before, you would do typical shear diagram. But okay, if you look, you plot the shear diagram. Are you watching, guys? Ini, saya quick one, bro. I'm not talking about question mark, but just to show you. Then you find the maximum at this plane is maximum moment is here. This moment at here. But also actually, if you look, you see this is the shaft orientation. This is the shear diagram. This moment. I believe you guys know how to do it because we already did this in previous class, right? This kind of example. We have shear diagram, we have moment diagram. But okay, if you look, the moment critical is here. Can you see the first one? Can you see nampak tak? The moment here is 10 to the power 6. But nampak the red line color. Actually, we are not taking at that critical area. We are taking at the shoulder. Can you see why is the shoulder? Shoulder means we have stress, concentration factor. Even the stress at shoulder, even why because we have moment, it means that at this shaft, they have bending stresses. But the maximum moment is not on the plane shaft where the diameter is 40. But yeah, because that is the maximum moment. Of course, this one will have the maximum bending stress at this point. But we are not taking at that point. This take note. I'm not taking. This is not considered still critical, but we are taking. Nampak the red line at the shoulder. Why shoulder? Because shoulder have stress concentration factor. Let me show you. Guys, Boleh tengok sini kelas. Can you see my live video class? Live video. I'm just to mention to you. Before I go to the next example, I'm not showing, just explain a little bit about this one. Class, are you watching?
Yes, doctor.
Yeah,
Yes,
because the
doctor.
shoulder, the rest of you, do you understand what I'm talking about? Shoulder, okay, you see, I've zoomed it. Okay, this one, diameter is 40. The shoulder diameter is 45. Here is the minimum diameter here is 40. Why shoulder? Actually, from the moment diagram, maximum moment is here because we have the force here, right? It's here is moment. So they have is critical here. This one maximum bending stress here. This one suppose we analyze, but I'm not analyze here. I analyze at the shoulder here. Based on moment diagram, since I know the value here, I can know the value here. Why? Shoulder, shoulder critical. Why? Critical than plane one. Even this maximum moment, this one is less maximum, close to maximum, but this is more critical. Why? We have KF, stress concentration factor. Why stress concentration factor? Because at shoulder, we have like this. Shoulder, when I zoom in shoulder, if you're looking at my video, shoulder, we have fillet. We have fillet. Okay, this is the diameter 40. This is diameter 45. When you have fillet, okay, we have a bending stress. At fillet, can you see the radius R? The radius R, D is small d. This is bigger D. T is the radius L or the fillet. At the fillet, the stress concentration of the bending is much. If I plot the stress, okay, this is neutral axis, the bending stress at the shoulder. Kalau typically at plane one, no shoulder, no stress concentration factor, you punya bending stress like this kan. Atas will go for tension, bottom will go for compression. Same value, neutral is 0. But when you have a stress concentration, the stress concentration distribution, the stress distribution is much longer. Can you see, compare this one, it kind of extended like this. And then at the neutral, it go like this. But here, this one, the shoulder at the bottom, right? Shoulder at the bottom, it extend, it kind of elongate. Understand that, class? Are you understand what I'm talking about? Class, do you understand? This value ni, they have multiplied the KT. KT is static stress concentration factor. This is KT. How to get that KT? You can go for table 4. This one I will explain not in this class, the next meeting on Sunday. But this one, our case, it means your stress that you will calculate in this case, you have to find the fatigue stress concentration. KF is 1 plus Q, KT minus 1. You have to find this. So your KF value, so how to find KT from table, from the figure on chapter 4, this one later I will explain to you. Q is the noise sensitivity, then you get the KF. But this KF, fatigue stress concentration factor, must multiply your sigma bending. Understand? Your sigma bending is kind of extended, multiply by the KF. But I'm not, our example that I want to discuss, we're not focusing, just plain diameter. Clear? Quick one. Okay, because this is introduction. You are still on part 1. Okay, class, just mention to you. I'm not asking you to do this, not discuss about this. I want you to check on this. The question number 3 is much simple one. Boleh tak, class? Class, are you watching? Question number 3. Question number 2, sorry, number 3. Are you watching, guys? Question number 2.
Yes, doctor, we
Yes,
can see.
doctor.
Yeah. Question number 2 is different because the question number 2, can you see the shaft no step, right? Question number 1, the shaft is shown, draw the shaft. The shaft have step. They have shoulder. They have shoulder here. But the worst is here. Yeah, this one that I show. But question number 2 is just plain shaft. Actually, it's much simpler. Just only plain shaft. Remember, you already did practice this. Of course, you can find direction and O and C. Betul tak, class? Don't tell me you cannot do this. The first free body diagram. Tahu kan? Class, we already did practice this last class. Because I don't have to show to you to calculate everything now because time very limited. Faham tak, class? The first thing, okay, it said that, okay, this is a shaft. The shaft is AISI1020 hot reel. Okay, of course, from here you can find the SUT. Remember, SN prime 0.5 SUT, remember? From here you can find your SUT. Because fatigue analysis, we no longer use SY. Clear tak, class? We don't use SY. We will use SN. But SN, CL, CG, CS, CT, CR time SN prime. SN that we need to calculate is CL, CG, CS, CT, CR time SN prime. Time SN prime, that will be your SN. Okay, Sn prime to 0.5 SUT. Of course, from here, you know what is your SUT value. Clear tak class? So you know your Sn prime, I cannot, how do you put prime, equal to 0.5 SUT value that you get above. Faham tak class? Clear eh? Okay. Okay. Assume that, okay, this one, I don't have to do that's why I like physical class. I can make it on the whiteboard, but since this online, just say it like this. Boleh tak class? Okay, you know this one, T1 is 0.15 T2. Remember already practice similar like this? T1 here is 0.5, is 0.15 T2. Kan? Class. Class, are you watching or not?
Yes, Doctor.
Watching.
All right. You boleh and the first thing, okay, they said this shaft is AI 1020, so you can get the SUT, you can get your SN prime. Okay, S roll, this one as mentioned is S roll, not hot roll, S roll. You can get your SUT, then you can get your SN prime. Assume the bed tension is 15% of the tight sensor. Okay, it means that okay, the tight tension is, sorry, not T1, T2, sorry, T2, my mistake. T2 is 0.5. Sorry, how do I erase ni? This one erase. Apa saya boleh conteng, saya tak boleh erase ni kejap Oh, this is text. Okay, sorry. Text is yeah, T2 kan? T2 is 0.15 T1. Betul kan kelas? So what you do, okay, first you solve the free body diagram like we practiced before. We can got, since T2 is 0.5 T1, summation of torque direction of X0. So that's the first thing. Kita make this summation of torque 0. TA plus TB is 0. So it means torque 1000 Newton second. D is diameter 200, radius is 100. Can remember, class? Okay, if you still not clear, first thing what you do, you summation. You look on my live video, class. My live video, top X, sorry, counterclockwise. So on this top X equal to 0. So it means positive X. So I have 1 to 100 times 100. Okay, 1 to 100 times radius of that pulley is 100. Minus 200 times radius of pulley is 100. Okay, plus, okay, T2 is going to positive X. T2 times 150, so will be 75 radius. Guys, do you understand I'm talking about, class? Minus T1, T1 will go for negative. This already, we already did this in class. Similar like this. Plus times 75 equal to 0. Plus, are you watching or not?
Yes, doctor.
Plus, are you there?
Yes.
So said it's mentioned T2 is 0.15 T1. So we got lah T2 is T1 T2 is 0.5 T1. Okay, yang ni they take yang mine is counter positive. It's okay, the same thing. So T2 is 0.5 T1. And from here, since T2 is 0.15 T1, if you look on my live video here, so we can get the T1 is 1.569 and T2 will be T2 will be T2 is 0.5 T1. T1 is 1.569. So T2 is 0.5 T1. Okay, T2 we can solve it. All right. So after you got this, then you can make the shear diagram and the shear diagram or the moment diagram from both plane. If you look here, the plane is like this. If you look at it, if you look at this picture, okay, if you look at this diagram, so that's why we have XY plane. So you make a shear diagram. Okay, this will be this is a torque diagram. So yeah, okay. If you look here, this is a plane XY plane. This is XZ plane. XY plane you have 1000 Newton. If you look here, this is your shaft XY plane. Okay, XY plane. So you have reaction at the scene we have at A, B, C, A, B, and C is bearing, A is bearing, right? O is bearing, O, A, B, C. So on this one, XY plane, we have 1000 and 200. So we have up is 1400 Newton. Okay, and we have, okay, but at XY plane, we don't have T1 and place T2 because that is in Z direction. Clear? But this up, the O must be bottom. We have OY, and this one is up. C is bearing, C also at the bottom. So we have CY. This one I don't need to show. You can moment at O, understand? Moment at we did before, so you can get this thing. So we can get this thing. So we have OY is What is the value? OY is, so because the solution, the way they code it. So we have the value of OY and CY. The value is there. Okay. So you can plot. So you can plot. So this will be like this. If you look diagram, and so this will like that. So become like this. So this will be your shear diagram. Shear diagram in Newton. And then of course moment will be like this. Newton millimeter. You can do this. Newton is like that. Class, are you watching? So this is your moment like that. Moment go to negative here at A. So at SY plane, A is critical. Class, are you there? The moment is SY plane moment at A is 178. Moment at A is 178,200 Newton millimeter. Class, are you watching? Class, can you hear me?
Doctor.
Yes,
Ini
Doctor.
you already done this class. I want you to look at this. To look at this. Kalau you practice exercise much better. But now we are okay. This is exact plane. Exact plane OABC. Okay. Okay. OABC. OABC. Can you see the figure? OABC. Okay. Exact plane. What do we have? Class. What do we have here? Are you watching my video? What do we have here? We are looking at the top view. Exact plane. Look at the axis like that, can we have x, y pointing up, z is pointing to the right here. So this is exact plane. We are looking at the top. So we have, okay, do we have at A, do we have any 1,200 plus 100? Do you have 1,400 written at A?
Oh.
Do you have? No. But at B, yes, we have. Plus, yes, we have. Can remember T1 and T2, we already solved it, already given. T1 and T2 already solved. T1 is, just now, whereas T1 is T1 15969, T2 is 0.15 T1. So you got the value of, so you got also, so this will be at B will be here. So if you look at the diagram, we only have T1 plus T2 and at B. T1 plus T2, we know the value. And the reaction at bearing, so this is downward, the OY, the OZ should be upward, OZ. And CZ should be upward, CZ. Right. So we know the value moment at O0, you can find CZ. So we know the value. So of course, when you plot the shear diagram, okay, the shear diagram, it will be like this. So it's up and by like this and go like that and go close like that. So this will be your shear diagram. This will be your shear diagram. When it goes for a moment, yeah, it goes for like this. Same moment 1, 2, it go up. Because ini negative, yang tadi exact ke bawah lah because negative area, this one positive area, go like that and go like that. This one you must know. We already discussed it in class. Something similar like this. Difference of moment is the area, right? So this is a moment at B, but here B is critical, but at X, Y plane, A is critical. So it means you have to check both. You have to check both. Okay. In this example, they don't have shoulder like I mentioned to you just now, fatigue, stress, concentration, because in this case, we just plane diameter. Just as introduction example to you, okay? Okay, class, nampak tak? You know how, this one you can solve it. You have shear diagram, moment diagram at XY plane, shear diagram, moment diagram at exact plane. So in this case, nampak tak? At XY plane, A is 178 negative side, but the value 178,000. But exact plane, at exact plane, moment at B, but B is critical. B is, moment at B here is 196,800. Okay, moment Newton millimeter. Okay, in this case, you understand what I'm taking. So you must know the value here. Now what the class? So you must check both total moment at A and total moment at B because we have two planes. Are you listening or not, class? Class, are you there?
Yes, Doctor.
That's how you do it. That's how you do it. Okay, so what you will do then? So here, you have to check both. Moment at A. Moment at A is moment at A XY plane square plus moment at A exact plane square. Tahu kan? Okay, moment at A at XY plane, we know 178,200 square. But moment at A exact, macam mana? How do you solve this thing, class? I know this is 196,800 and I know all the distance here. You boleh solve this thing. Theorem Pythagoras, you know that? You know theorem Pythagoras? What do you call this thing? Class. Can you solve this thing tak? You know the distance here kan? You know all the distance of the shaft. You know the distance here is 200, 200, 200, 150. Same goes here. Can? Ini 200, 200, 150. Okay, moment at A, okay, this is point A, but this is exact plane. You make straight line. You know this is a straight line. But what is the value here? Of course, you know this thing. Macam mana you solve it, class? Theorem Pythagoras, class. This is, here is 196,800. So what is the value here? Need 200, 200. How do you solve? How do you get the moment A at here? Class, are you watching or not?
Yes.
Of course, you know, can 196 over the total is 400. Okay, 196. We need to value, you need to find this value. This over 100, 196, 800 over 400, because this total 400 equal to, this is moment at A exact plane, right? This is the value moment at A at exact plane over 200. Betul tak, class? Class, are you there? This one over this length, moment A over 200 equal to this one moment at B 196 over 400. That's how you got. So you got your MA at exact plane. It's already mentioned here. It's already mentioned, already stated. So this moment at A is 98,400 as already. Can you see there? The value is there. Class. Ni, 98,400. Do you understand or not, class?
Yes, doctor.
Yes, doctor.
Yang lain. Yang lain tu jangan tidur pula. Yang lain tu sleeping ke? Wake up, wake up. Come on, wake up. So moment at A plus moment at exact plane is 98,400 square. So you got the value ini. This one, look at the solution. Okay. So you got 2.036 times to the power 5 Newton millimeter. Okay, moment at B also you have to calculate, because we have to take the summation moment as y square as z square at both points. Okay, moment at B also you must calculate moment at B. So from moment at B is here. Nampak tak? SY plane we can, it's not stated, but we know a straight line. Same method. Look at my live video class. So how do you get this moment at B at this SY plane? How do you get it? Moment at B over D is 150 over 150 equal to this one, the value 178,200 over 200, 350 equal to 178,200 over 350. So you got your moment B. This is theorem Pythagoras, basic guys, basic mathematics, geometrical. This is supposed to must know. This was 150. All right. So moment at B is, as stated here, is 76. Moment at B here is 76,350. 76,350. Nampak? As XY B is 76,350, but as Z plane we know 196,800. So moment at B, you have to cut total moment at B is moment at B XY plane square plus moment at B exact plane square. Faham kelas? Ni kelas online itu sebenarnya tak gemar sangat kelas online, tapi nak buat macam mana? Kelas, are you there?
Yes, doctor.
Yes. Yes.
Right, good. All right, so kita just substitute value. So moment at B will be SY plane 76,350 square plus moment at Z exact plane, we know it, 196. Moment at B is 196,800 plus 196,800 square. So the value is 2.111 times 10 to the power of 5 Newton millimeter. Which one is the bigger, B or A, total moment? Cepat kelas. Kelas, which one is bigger? Cepatlah kelas. 352 dah ni.
Moment
Saya
at
buat
B
sampai,
is
saya buat sampai pukul 5 kau marah pula. Ha? Which one is bigger? Check betul.
B.
B. Can you see the ni, the PDF ni? This one. I'm sharing or not? I'm sharing my ni kan, PDF kan? The solution. Guys,
Yeah.
which one bigger, A or B here? Ni dengan ni dua ni, mana which one bigger? Tengok check betul. Which one?
B,
A or
doctor.
B? B, little bit slightly bigger, 2.11. Can you see that? B is critical. Nampak tak? That's why you have to be careful. Kan? You mean the shaft tu jadi just now. Kita ada A here, A pulley A, as smaller pulley B. Sometimes we thought they said no. You have to check. Understand tak? This is how we do it. So B actually is bigger than A. Total moment, moment SY plane square plus moment SZ plane square at B. So B is our point we need to analyze. Faham tak kelas? Clear? So B, this is B, the moment. Betul tak? Kelas, are you there?
Betul.
Yes, Doctor.
Okay, then kita tahu moment, kita calculate apa? What stress?
Bending stress.
Yes, bending stress at B. So at B, B is critical. Understand? You know where is B? Where is B? Where is B? On the shaft. Which one? Where is B? On the pulley, smaller pulley, right? Can? That one is more critical. Highest bending because moment there is much greater. Highest bending moment. Do we have any torsioners? Okay, be careful. Do we have axial stress at the shaft?
No.
Do we have axial? No. Do we have torsional stress? I need to ask you. Torsional stress acting between what? Can you see the torque diagram? A and B have torque.
In
After
A
B,
and
no
B.
torque. But we have, at the border FB, we have torsional stress, kan? Like the one we did practice previous class. Betul tak? We have torsional stress at B. Understand? This is a torsion diagram. A and B. But after B, we don't have it. All right? Okay. Okay, now at B, but the critical bending moment is at B. So bending moment, sigma bending, are you watching my live video? 30, excuse me, sorry. 32 moment. Okay, 32 moment. Ini shortcut untuk solid round kelas, solid round shaft. Okay, 32 moment. Actually MC over I, 32 moment over pi d cube. This is bending stress, right? Moment at B. Betul tak kelas? Kan? Kelas? Kelas, are you watching or not? So
Yes.
moment at B tu berapa? 32, moment at B berapa?
2.11.
2.111 times 10 to the power of 5 Newton millimeter over, okay, pi, okay, diameter ni, be careful. Diameter apa? What is the diameter? What is the diameter at B?
150.
All the shaft is plain diameter kan, 25. We don't have stress concentration factor because this simply plain shaft, no step, even no notch. Notch nanti next class kan. Notch they have a groove, yeah. No notch, no groove, just a plain shaft. Okay, we don't have stress concentration factor. Okay, diameter of shaft is 25. I mean the whole A or ABC, the shaft is 25 meters. So this is 25 to the power of 3 millimeter cube. So we got sigma bending. So we got sigma bending is lagi 4 minit. Boleh saya extend lebih sikit masa boleh kelas. Okay, apa ni? So we got the bending stress is berapa? Bending stress ini. So bending stress, so you got here the bending stress is okay, sigma bending is 137.6 megapascal. Okay, ni bending stress. Okay, bending stress. Right. Okay. Okay. What about torsional stress? Do we have? Yes, we have torsional stress at B, right? At B torsional stress berapa? At B torsional stress berapa? Ini bending, bending. Torsion stress. This is bending stress. Torsional stress. What is the formula torsional? Tau is 16 E over pi d cube. So what is the value of torque actually? Torque actually is already calculated just now. What is the total torque berapa kelas? What is total torque? If you look here, what is total torque? 1,200 Newton times the radius times 100 minus 200 times 100. Total torque is, because it must pulley A produce the torque, balance B will be the same value but reverse. It will cancel. Total torque is 1,200 times the radius of the bigger pulley times 100 minus 200 times 100. That will be your total torque. Okay, the total torque. So torsional stress is, as shown here, torsional stress is ini. Torsional stress is berapa?
100,000.
Torque. Torque is berapa?
Yeah, 100,000.
Jadi 100,000 kan?
Yeah.
100,000 1000 is Newton millimeter. That is where total torque. You put the value here. That will be your total torque. So you punya torsional stress is, nampak tak dalam solution you ada KF kan? Your KF tu semuanya value dia 1 because kita tak ada. 1 is no stress concentration kali 1. Nanti kita discuss yang the other question where we have shoulder and yang ada shoulder, but this one is 1. Okay. So torsional stress is you put into this value. So you got torsional stress is 32.6 megapascal. Okay, 32.6 megapascal. Are you watching class? Are you still watching class? Class, are you there?
Yes, yes.
All right. Okay, another thing to mention to you. Okay, remember, as I mentioned to you, for fatigue analysis, we not simply calculate stress like that because our tengok sini class. Are you watching my live video? Our bending stress plot dengan time, is it straight line or is it curve? Is it sine wave or is it just plain one? Bending stress. Can you see the shaft is rotating? The shaft is rotating. It said that the shaft is rotating because we are it doesn't say in the question, but it's fatigue analysis. Because always running by motor, the shaft is rotating. Okay. Kita need to determine based on infinite life. So it means high cycle, 10 to the power 6 cycle. It means the shaft to rotating high revolution. We want design it to be infinite life. Based on, it means 10 to the power 6 and above cycle. That's why we use yang tadi SM tadi, the endurance limit. Understand tak, class? So now, the bending stress. How do we plot the bending stress against time, class? Here, my live video macam mana?
Sine wave.
Sine wave, yeah. Sine wave dia macam mana? Bending stress, sine wave dia macam mana? Is it like this, above, or is it on negative side, or is it this time completely reverse? Positive and negative, the same value, and the mean is 0. Which one? Which one? Which one? A, B, or C? Which one? Cepat sikit. For bending.
C.
A, B, or C?
C.
Can you see? The shaft is rotating. The shaft is rotating. As I told you, the shaft is rotating. And we have pulley, D is the element. B is here and B. The shaft is rotating. And up, it can face tension. Bawah, it go for compression. Up tension, bawah compression. Up tension, bawah compression. Can? Because the shaft is rotating, it means the element is rotating. If I look at the side, because since section B is critical, up is tension, then the shaft is rotating, it go for compression, tension, compression, but the value is the same. Atas tension, bending stress, positive value, but it goes down, compressive stress in compression. Understand, class? Because the element is rotating. So the element, because the shaft is rotating, so the element will face compression and tension by the same value. So the plot of the graph will be what? A, B, or C?
B.
Yes,
C.
it will be C. Not A. A is wrong. B, more compressed, wrong. It facing completely reverse. Nampak? Positive, tension. Bottom is compressive. Betul tak, class? Bending. Bending stress. I'm not talking about torsion. Clear?
Yeah.
Clear or not?
Data.
Completely reverse. For bending is completely reverse. Okay, bending through time is completely reverse. Can completely reverse. Betul tak? So because the idea we need to find what is the sigma amplitude, what is the sigma mean for bending. For bending, sigma mean berapa? Bending. Sigma mean berapa? Mean.
0.
Zero.
For amplitude, apa value amplitude? We already calculate. Betul tak? Betul tak, class? We already calculate. 137.6, the 32 moment at B, pi d cube. Betul tak, class? This one. 137.6 megapascal. That is amplitude. Alternate. Betul tak? The alternate or amplitude because the alternate value. Clear?
Yes, doctor.
Right. That will be your, okay. But now I am asking you about torsional stress. We have at B, we have torsional stress. Okay, what about torsional stress at B? At B, torsional stress tu macam mana? Logically, okay. Class, tengok sini. Ini the big pulley. We have big pulley A, okay? And this is the shaft now. Pulley at OA. And here is the At the back we have small pulley, but the B2 critical bending, small pulley here. So the dia punya loading tadi macam ni lah. We have torsional stress. So we have torque 1, torque 2, we know the value, we already calculated. So we have like this, 1,000, 100 volts is up, 1,200 and 200. Okay, at B we have torsional stress. Okay, we have torsional stress. Okay, this is the torsion right here is this direction, the direction of the torque. At B, D is T1 is bottom, D is T2. Sorry, so T1 is bigger, so direction is like this. Okay, at B we have torsional stress. Okay, logically at element, if you want look at my live video, so this is section B. So we have torsional stress like this direction. The shaft is rotating. This is your torsional stress. All along the circumference, the torsional stress value the same saja. Macam bending, atas top is tension, bottom is compression. That's why I go for sine wave completely reverse, right? But for torsion stress along either up or bottom along the circumference, while the shaft is rotating, the torsional stress remain the same value, 16T over pi d cube. We already calculate. So what is the plot of torsional stress against time? Now I need to ask you, if you are listening to me. What is the plot of the graph torsional stress against time? Is it sine wave or is it straight line? As I mentioned to you, torsional stress, even the shaft is rotating, remain the same. No compressive, no tension. Same value of torsional stress. Remember guys, 16T over pi d. We already calculated it, right? Torsional stress tadi we calculate is berapa megapascal is torsional stress is 32.6 megapascal. So this 32 megapascal torsional stress against time, how the torsional stress against time. So what is the plot? Class, are you watching?
Straight.
Sine wave ke straight line?
Straight.
Yes, good. Straight line, positive, right? The value is 32.6 because even it's rotating, the torsional stress along the circumference, you were rotating up and down, and it remain the same value, 32.6. It's not changing, right? It's not fluctuating, the same value. So it's a straight line. Okay, if torsional stress is straight line, what do we have? Do we have tau mean? Do we have tau alternate?
No.
What is tau alternate? Tau alternate is 0, right? Because we don't have sine wave, no alternate value. But what about tau mean? Do we have value? Purata. Average. Yeah, this is the tau mean, right? Tau class. 32.6 is the mean. Remember, tau mean, tau max minus tau minimum over apa? Over 2 kan? Plus tau mean, the mean value. And tau max is the true, sorry. Tau, what is mean means what? Mean means tau max over mean means what? Tau apa? Sorry, mean mean plus. Sorry, sorry. Plus, sorry. Mean plus, Mean plus. Sorry, that is amplitude. My mistake. Okay. Tau max minus plus tau mean over 2. Betul lah kan? Since tau max and tau minimum is the same, bagi 2 is that value lah. Betul lah kelas? But tau alternate, since tau alternate is tau max minus tau mean over 2. So we don't have, since this is the same value, so we got 0. This is not alternate, because alternate is the value can alternate when you have a sign like this. This is your neutral axis. This is the value of your alternate, right? But in this case, we don't have alternate. We only have the mean value, all right? So tau mean is the same value, 32.6. Understand? Okay, so that's what you mean. Okay, what's the point? Okay, the point is, sigma bending is now. For bending, we have amplitude, okay? For bending, we have amplitude, but mean is 0. But for torsional stress, we have mean, but we don't have alternate. We don't have amplitude. We don't have, sorry, alternate. But mean, for bending, we have alternate, but the mean is 0. But for torsional stress, we have the mean, but the alternate is 0. Okay, so in this case, okay, if you look the textbook, look in the textbook. Okay, sorry, I a little bit extend masa sikit. Okay, if I stop sharing. Okay, hold on. Okay, let me share you again the textbook. The textbook. Not this one. Textbook. Mana textbook? Okay, let me share you. Can you see the textbook ni? Yang table 8.1, guys? Guys, are you there?
Doctor.
Ada kan? Textbook,
Yeah.
Alright, textbook. Okay, how to get, okay, because we know the both condition of mean and alternate or bending, and both condition of torsional alternate and bending. So, because remember, as I told you, that we need to find, okay, to get that sigma EA, can you see? Okay, this is important. You take note under this table 8.2. Table 8.2, you must know this equation. Take note on this page 3 to 7. Ini penting. Okay, this is important. Okay, this is how sigma EA and sigma EM. Sigma EA and sigma EM. That's how you calculate your sigma EA and your sigma EM. Because we need to find the total equivalent, because our certificate factor is Sn over sigma E. So which one sigma E we need to ni lah. Sigma EA and sigma EM. Okay, in this case, sigma EA is the sigma amplitude plus 3 tau amplitude, right? Sigma EM is a sigma mean over this one, all right? Okay, that's why in your, hold on, if you look on the way you find safety, okay, sigma, dapat the value here, sigma EA and sigma EM, so you can find the safety factor is like this, plus the safety factor is like this. Okay, first we got to find the sigma EA. Sigma, if you look on the textbook, okay, sigma EA, guys, are you watching or not? Okay, look, sikit lagi tu,
Yes,
okay,
doctor.
right. In our case, this equation, sigma EA equal to square root sigma amplitude square plus 3 tau amplitude square. Because our case, as section B, we have both bending and torsional stress. Okay, sigma, we need to find sigma E equivalent amplitude. Okay, sigma equivalent alternate. Alternate, EA to mean alternate, and sigma EM. Sigma E alternate, we combine both bending stress and torsional stress. Okay, remember, bending stress, do we have sigma alternate tak tadi? Bending stress, okay, I show you this figure. Bending stress, do we have alternate?
Yes.
Ada kan?
Yes.
Yes, we have bending alternate. Okay. Okay. Tau torsional stress at B. Do we have alternate?
No.
No, straight line, no alternate, 0. So this one will become 0. Faham tak? We only have sigma E equivalent alternate equal to sigma that we calculate. Betul tak? So what is sigma alternate? We already calculate sigma alternate tadi. Bending stress is 137.6 megapascal. Betul? Okay, that's the point. Okay, sigma EA, we already find it. All right. Okay, sigma equivalent mean. Because earlier I mentioned to you, kan, we want to find the mean and also alternate. Sigma equivalent mean, the equation given the textbook, you must take note, you highlight this thing. Sigma mean over 2 plus square root tau mean square plus sigma mean over 2 square. So this is the equation. So we just substitute. Okay, because sigma is always for bending. For in our case, sigma that we have only bending stress. We don't have excess stress. Sigma, okay. Sigma bending, do we have for sigma bending tadi? Do we have apa tu?
Oh.
Bending tadi. Mana figure? So I want you to be clear. For sigma bending, do we have mean? Completely reverse, right? Mean is 0, right? So this one becomes 0 because bending 0. Tau mean, do we have it? Yes. Kan? Torsional stress is constant. That is mean 32.6. Yes, we have this one. Yes, we have 32.6 megapascal. Sigma mean also 0. We don't have bending because bending under our bending stress mean is 0. Clear tak class? So you substitute into this value. So sigma EM equal to tau mean kan? Because this 0 and 0 equal to tau mean. So equal 32.6. So in our case, sigma equal because our safety factor Sn over our sigma E by the denominator, but we must focus on sigma EA and sigma EF, amplitude and minimum. So how do we put into what equation? Okay, the equation is like this, guys. The equation is like this. The equation 2 for your actually is not, sebenarnya guys, your equation is actually bukan, as I mentioned, actually I just give you for the, I mentioned to you Sn over sigma E. Actually it's not sigma E. We must focus on sigma amplitude and sigma E alternate and sigma EM that we just calculate just now. Here, this one. So how do we put here? So the equation is like this, guys. So safety factor for, okay, dia ada teori ya, dia ada teori. So dia punya equation dia, if you look on the solution, it's already shown to you. Okay, can you see the solution, class? Class, are you there?
Yes, doctor.
Doctor.
Okay, the solution is like this. Sigma EA amplitude that we calculate over the endurance limit plus sigma EM that we calculate over the SUT equal to your 1 over your safety factor. This is based on Goodman. Yang ni yielding. Dia ada two pattern. Nanti next class kita discuss about this theory. This is based on Goodman. You always use Goodman punya formula. So this is important. So this is your safety factor. 1 over n safety factor equal to sigma E over Sn. Sn we already calculate just. Okay, Sn where I've not shown you how we calculate Sn tadi. SUT we must know. Sn we can calculate. Nanti I show you. Sigma E we already have here and sigma EM already have here. Okay, now SUT we can get 0.5. SUT we can get from table properties. Sn, so Sn we have not calculated yet. So what is Sn? Sn, as I mentioned to you, is Cl. If you look at my video, Cl, Cg, Cs, Ct, Cr, Sn prime. Okay, look careful. Sn prime is 0.5 SUT. Okay, I need to be quick, guys. A little bit saya extend masa sikit. Alright, because Selasa kita tak ada kelas. Alright. So Sn is 0.5 SUT. So in the question given that it is made of 1020 S roll. 1020 S roll. If you look in the buku table properties. Okay, if you look buku table property appendix C. If you look at appendix C here. Let me rotate it. Boleh nampak textbook? Boleh nampak? Am I sharing textbook or what? Boleh kan?
Yes, doctor.
Plus, okay, 1020 S roll. 10, apa tadi? 1020 S roll kan? 1020 S roll. So you go at table appendix 3, 1020 S roll. Can you see guys ini? Nampak tak kelas? 1220 S roll, appendix C4A. So you're not finding the yield strength, get the tensile strength. This is SUT. Okay? Ini adalah SUT, tensile strength, ultimate tensile SUT. Okay? SUT. This is your SUT value. Tensile strength S roll 448.2. Nampak tak kelas? Are you there, kelas? 448.2. Okay? 0.5. So your SUT tadi adalah 448.2 megapascal. Megapascal 0.5 or 448.2. So you got your SUT is as shown in this solution tadi. Tadi yang ini dia dah calculate awal tadi Sn is 224, Sn prime 224.1. Okay, Cl is 1. Why Cl is 1? Because Cl is the load factor because bending. Remember, kalau you go for textbook, kalau you go for chapter 8, okay, chapter 8 balik, okay, kalau you go for back to chapter 8 tadi for ni, load factor, as mentioned tadi, ni load factor, boleh nampak kelas table 8.1, load factor bending 1. So Cl is 1. Cg is gradient factor, size factor. Diameter of the shaft is given that just now. The question diameter of the shaft is, the diameter of shaft is 25 millimeter kan? Diameter of the shaft is 25 millimeter. So in your textbook, 25 millimeter, class, are you watching in class? Apa nak saya cakap ni? Boleh buat lagi sikit lagi kelas.
Boleh, Doktor.
Boleh, Doktor.
Well, the diameter of the shaft is 25 meter, is between this range, between 10 to 50, so 0.9. Okay, so because kita bending, why bending? Because bending is the highest compared to torsional stress. Bending stress, actually we got it is 137.6. Torsional stress is only 32.6 megapascal. So bending govern bending. So what's here? You use the first column. Kalau torsional stress that you get greater than bending, you will use the third column torsion. Understand? Clear tak class? Because bending stress 137.6, torsional only 32.6. So bending stress govern. So we based on bending, right? So the CG is 0.9 because 25 millimeter. Okay, surface factor. Okay, be careful. Surface factor, look at figure 8.13. Figure 8.13 here. Okay, this is figure 8.13. Let me erase ni. Okay, what is your SUT just now? SUT berapa? 448.2 kan, class? Are you watching or not, class? SUT is 448.2. So it means 0.4, close to 0. This is 0.5, 0.448, 0.4. This is 0.5, 0.45. Lebih kurang sini. I cannot draw it right perfectly, but you bring it up, straight line up till ini because this is machine. Class, are you watching or not? Class, somewhere here. Class, are you watching?
Yes, Doktor.
Class.
Yes,
Yes,
Doktor.
yes. Watching.
0.45 here, 0.5 between 0.5. So you pakai straight line, you just bring it like this, up until they intersect with the machine. Because always machine, unless it is given. The question always will be, normally kalau not, always machine. You said that, okay, that you said the shaft is machine. Can you see the shaft is machine? Machine mean or quadrant. Intersect with line machine, and it is 0.79. So the answer is 0.79. If you look the solution, it must be 0.79. Your CS is 0.79, betul. Okay, CS. So you have your CS is gradient tadi berapa? Gradient is 0.9. Surface factor CS is 0.79. Okay? Okay, CS is 0.9. CR is a reliability factor. Now we have reliability. CR is reliability factor. Reliability factor is CR. CR reliability factor. Kalau it's not given, is 1. Guys, kalau mention 90%, mention the question, you use this one. But if it's not given, it's not given, or it did mention, it's not mentioned always is 1. Okay, 50% reliability. Okay, kita 50% reliability. So it means the CR is 1. Okay, so your CR is 1. Okay, your CR and temperature. Temperature is not given, always we use 1. Unless temperature is high enough. You didn't mention any, so temperature we can use 1. But if you given, you must use this one. Temperature you put into, but it's not given less than 40 degree, 1. Based on bending, as on torsion is the same, 1. So your CR and CT is 1. CR is 1, CT is 1. So you just substitute into the value. So your total SN is 0. Load factor CL is 1. Gradient factor is 0.9. CS factor 0.79. Your CT is 1. CR is 1. All right. And times your SN prime. Times SN prime is 224.1. So you got your endurance limit is if you look on the solution, your endurance limit, you already calculate. Actually, they already calculate at the beginning. I buat ni after ni the last one. 159.3 megapascal. So this will be your nominator, you put into this equation. This is the equation using Goodman theory. This is Goodman line. Based on Goodman, so this is the, so your safety factor like this. So if, because this is the equation, okay, the equation is like this. Okay. Safety factor. So sigma EA we already calculate just now. Sigma EA is just our bending stress. So safety factor, safety factor is sigma EA over SN. SN we already calculate 159.3 plus sigma E mean over SUT equal to 1 over safety factor. This is based on Goodman theory. Goodman theory. Goodman theory, this is safety factor. So you put, so what is the safety factor? Okay, sigma EA we already calculate just now. Sigma E alternate is 137.6. Sn, we already calculate Sn just now, 159.3, and Newton's limit, 159.3 plus sigma EM. Sigma EM kita tadi just now based on to equal to torsional mean is 32.6 over SUT. SUT from the material that we study, SUT is 448. SUT is 4 from the table properties, 448.2 equal to your safety factor, Goodman. So NG, so NG means Goodman theory. So this is your safety factor. Class, do you understand, class? Are you watching or not?
Yes.
Substitute the value. So
Yes,
you
Doctor.
safety factor. So you can solve safety factor from here is safety factor is 1.94. So it means it's safe. So this shaft is safe based on fatigue analysis, based on infinite life. Infinite life, I mean this shaft will survive infinite life. 10 to the power 6 revolution, cycle to revolution, one rotation or shaft to one revolution. Even 1 million revolution and above, the shaft safe to the point. Faham tak? Dia selamat. Infinite life. Clear tak kelas? That's how you do fatigue. You find fatigue safety factor based on fatigue analysis on the shaft. Okay, right? Okay, why this formula ni later next class meeting I explain why the equation is like that. There is a reason at the plot of the graph. Nanti I explain to you. So, but it's basically I show you one example how do we calculate the fatigue analysis on the shaft. This is a simple problem because the shaft two just plane. Another example we discuss nanti on the next meeting. The shaft two step. We have shoulder. We have stress concentration factor. Okay, class. I hope you understand. What I already explained to you. I think I did record this video. Maybe I share in the YouTube later. You can watch it. Okay, class. Any question before I go for attendance? Class.
No question, Doctor. Thank you.
Okay, let me share the
No,
attendance.
Doctor.
Hold on, jap. Okay, selamat menyambut Hari Raya Aidilfitri. Maaf zahir dan batin. Hold on, jap.
Selamat Hari Raya.
Thank you, Doctor.
Hold on for your attendance.
Thank you, Doctor.
Welcome. Okay, class, scan your attendance. Do I share the? No, I'm not sharing the ni. Hold on. Let me share the. Okay, class. Scan your attendance. Okay, selamat Hari Raya. Maaf zahir dan batin.
Thank you, Doctor.
Welcome.
Thank you, Doctor. Selamat Hari Raya.
Selamat Hari Raya.
Thank you, Doktor. Selamat Hari Raya.
Doktor.
Thank you, Doctor. Selamat Hari Raya.